Alright, I'm apologizing in advance for the length of this video, but I'll try to go through it as quickly as possible and so that it makes sense to you. So right now we're going to be talking about covalent bonding. I'm going to start just with some of the basics. Covalently bonded compounds are also called molecules. So you might hear molecular bonding um, or covalent compounds, same thing. Um, we already talked about molecular formula and empirical formula at the beginning of the year. If you don't remember, it is in your fall semester folder on Echo, as well as in the review for first year chem. Okay. If you remember, covalent bonding occurs when we share electrons to achieve the octet. So remember, the octet is all about being stable, but in covalent bonding, they share the electrons versus ionic, where they actually transfer the electrons. Okay, so what we actually have in this picture is the positive nucleus that are repelling each other, and the electrons themselves repel, but because of the attraction between the electrons to the nucleus, that's how they're able to be held together. So here's some examples of Lewis structures that I know you guys know how to do. So if you want to practice just to kind of refresh your memory, go ahead and pause the video, give yourself a few seconds to practice, um, and then I'll go ahead and show you the answers. So hydrogen, remember, only needs 2 electrons to be stable since it only has the 1 energy level, so they only share their 1 valence electron. The ones where we use the dots are the Lewis structures. The ones where we use the line to signify the bond is the structural formula. Okay, so Cl2, HF, H2O, and CH4. So also remember that the lines represent the bonds, whereas the other ones are non-bonded electrons, or lone pairs. So methane has 0 lone pairs, all electrons are shared. Water has 2 lone pairs, 2 bonds, 3 lone pairs, 1 bond. This one has a total of 6 lone pairs on the molecule, 3 on each atom, 1 bond. To make it a little bit more challenging, we have O2, which is how we find oxygen in the atmosphere, as well as N2, which is how we find nitrogen in the atmosphere. Again, feel free to pause the video so you can practice. O2, in order to achieve stability, does have to share twice. So it's a double bond where it shares actually 4 electrons instead of just the 2 electrons. Each line represents 2 electrons. To achieve stability, and if you check around each oxygen, it would be 2, 4, 6, 8, 2, 4, 6, 8. Nitrogen, however, has what we call a triple bond, where it shares 3 pairs of electrons for a total of 6 electrons to achieve stability. This part shall be reviewed for you. So if you're having trouble, check out some of the review from first year chem. Alright, so multiple bonds. Now, when we have more bonding going on, we have a shorter distance between the atoms and we consider it a stronger bond. It's like we're holding on tighter. So if I was there, Carmen, I would probably use you as an example, or Giselle, whoever's in the front. You know how I do. Okay, so if we have a single nitrogen bond, the distance that we have between the atoms is measured in angstroms. That's what this A with the little dot is. So that has a measurement of 1.47, whereas a double bond is 1.24, and a triple bond is 1.10 angstroms. Okay, so the more bonds there are between atoms, the stronger the bond is. You might also see it written as bond order, where it's in the first bond order is a single bond, second bond order, a double bond, third bond order, triple bond. So I know you guys know how to do Lewis structures, but I'm going to show you another way that you can do it that'll help with a little bit of the more obscure molecules that we'll be doing in AP Chem. So that's what this procedure outlines. So you write the sum of the valence electrons from all the atoms and take into account the overall charge. So sometimes we have those pesky ions. So you need to take into account the ions. Okay. You write the symbols for the atoms and show which atoms are attached with a single bond. So remember, a line represents 2 electrons. Then you complete the octet around all the atoms that are bonded to that central atom. Whatever electrons you have left over, you place on the central atom, and if there's not enough electrons to give the central atom an octet, that's when you need to try multiple bonds. Okay, so what I'd like you to try to do is phosphorus trichloride, PCl3. I'll walk you through verbally because I'm sorry I'm rushing this video. Um, So hopefully you recognize that phosphorus is our central atom. So it has 5 valence electrons. Chlorine we know has 7 valence electrons, but there's 3 chlorines. So times 3, that's 21 plus the 5. That's a total of 26 valence electrons that we need to put on this molecule. Okay, so you start with P in the center, then you single bond it to each chlorine. So that's 2, 4, 6 valence electrons that you've drawn so far. Then you complete the octet around the attached atoms. So that's around each chlorine. They each need 3 more pairs, 2, 4, 6, 8, 10, 12, 14, 16, 18. Plus the 6 you already drew, that's 24. So you have 2 leftover electrons that you put on the central atom, which is phosphorus. And when you do that, you do complete the octet around phosphorus. So you're done. BrO3 is the bromate ion. Bromine has 7 valence electrons. Oxygen has 6. There's 3 of them. Times 3 is 18. Plus 7 is math. 25. Plus this 1 electron, because it has a negative charge, so we have an extra electron, is 26. So you do the same process. Pause if you want to. Keep in mind that it is an ion, so we put the molecule, the Lewis structure, in brackets with the charge outside so that we recognize that it does have an extra electron compared to what it normally would if we just looked at the atoms. Now the reason I want you to get in the habit of doing this is because we can start having some funky things. Okay, so what we could have is multiple Lewis structures. So some compounds you can have different Lewis dot structures that follow the octet rule. So what we have to do is we have to use what's called formal charge to determine which one of those structures is the dominant Lewis structure, which one is most likely to occur most often. Okay, so a formal charge, again, they're not real charges, but they're the charge that the atom would have if the electrons were shared equally. Okay, so they're not real charges. It's really easy to figure out. The formal charge is equal to the valence electrons of the atom minus half of the bonding electrons minus the non-bonding electrons. Okay, so a formal charge is 0 for all neutral molecules and of the total molecule, and the formal charge of a polyatomic ion is equal to the charge of the ion. Okay, so that's for whole molecules. For example, if you draw out CO2, there are 2 Lewis structures possible. The first one is this. 1, 2, 3, 4, 5, 6, 7, 8 around carbon, 2, 4, 6, 8 around oxygen, 2, 4, 6, 8 around oxygen. But another possible structure that also satisfies the octet is like this, where we have a single bond and a triple bond. 2, 4, 6, 8, 2, 4, 6, 8. All the octets are satisfied here. So in order to figure out what the dominant Lewis structure is, which one we're most likely going to see, we try to figure out which one has atoms with formal charge close to 0. We also look at when a negative charge is on the more electronegative atom, that's more dominant than when a negative charge is on a less electronegative atom. So there's a couple things that we need to look at. Okay, so if we look at this first carbon dioxide molecule, to do the formal charge, we figure out how many valence electrons the atom normally has. So oxygen normally has 6. Then you take 1/2 of the bonding electrons. So for me, honestly, it's easier to just count, well, this is 1, 2, because really there's 4 bonding electrons divided by 2 is 2. So 1, 2, and then each single lone electron. So 1, 2, 3, 4, 5, 6. Well, 6 minus 6 is 0. So oxygen has a formal charge of 0. Carbon has 4 valence electrons. And so 4 minus, it only has bonding electrons. 1, 2, 3, 4. Formal charge of 0. Oxygen is identical. This oxygen is identical to this oxygen, so it makes sense for its formal charge to also be 0. So all the formal charges on this version of carbon dioxide are 0. On this carbon dioxide, we have 6 valence electrons minus 1, 2, 3, 4, 5, 6, 7. So this one actually has a formal charge of -1. carbon has a formal charge of 0, and this oxygen has a formal charge of, let's see, 6 minus 1, 2, 3, 4, 5, positive 1. So when we're looking at these, again, they're not real charges, but they help us figure out which one is the dominant structure. Again, we look for the ones that have a formal charge close to 0. Well, the formal charge on all of these atoms is 0. This is our dominant structure. One more example would be the formal charge of the Lewis structures for the thiocyanate ion, which is NCS negative. There are 3 possible Lewis structures. Go ahead and pause the video and see if you can figure out all 3 structures. This is what you should have gotten, and again, since it's an ion, we do have it in brackets, signifying the charge. Alright, so let's figure out the formal charges of the atoms within this. Nitrogen has 5 valence electrons normally. So we have 5 minus 1, 2, 3, 4, 5, 6, 7. That is a negative 2 charge. Carbon has 4, 1, 2, 3, 4. That is a formal charge of 0. And then sulfur has 6, 1, 2, 3, 4, 5. That is a formal charge of +1. Okay. Now if we look at the second one that I have here, nitrogen is 5 minus 1, 2, 3, 4, 5, 6. That's a -1. Carbon, 1, 2, 3, 4. That's a 0. Sulfur is 6, 1, 2, 3, 4, 5, 6. That's 0 as well. Okay, so already between these two, this one is going to be more likely because we have the formal charges that are closer to 0. Okay, let's check this last one out. Alright, so we have nitrogen is 5, 1, 2, 3, 4, 5. So we have formal charge of 0. Carbon again has a formal charge of 0. And sulfur has 6, 1, 2, 3, 4, 5, 6, 7, -1. Okay, so I'm already going to go ahead and mark out this one because it's the least likely with formal charges so high. We want to try to get those closer to 0. But if you look at these ones, the only difference is the sulfur has the -1 or the nitrogen has the -1. So what we have to remember is that we want the negative charge on the more electronegative atom. Well, it turns out our more electronegative atom is going to be nitrogen. Okay, so we want the nitrogen to have the negative charge. So this is going to be our answer, our most dominant molecule. That doesn't mean this one doesn't exist. This one is just much more likely and we'll have much more of it. Okay.